Hello everyone, welcome to my channel. This video is about how to extract latencies from the Linux kernel, and we would be using the PLY tool for this. PLY is a tool based on BPF. BPF is a tracing infrastructure, very powerful. It's used for online tracing in the kernel, and you can have a stable BPF since, in my experience, kernel version 4.19. Well, before that, we also have BPF available. It's very old, relatively old, but um, from 4.19, the extended BPF is relatively stably available in all Linux kernels with all the features. PLY is a tool that lives, a fork of this lives on the IOVisor GitHub project, which is heavily invested in promoting BPF related tools such as the famous BPF trace, the BCC, and some very nice documentation here. It has its own GitHub as well. It supports major architectures such as ARM and PowerPC and x86 64-bit, and it's relatively easy to install. Now, the good thing about PLY is that, well, you probably know that there are other powerful tools out there that use BPF. These are front ends, let's say, for BPF, such as BPF trace, right? But they have some dependencies. So, for instance, they require the LLVM compiler to be available. But PLY has the minimum set of dependencies because it only relies on the existence of libc, and that's it. So very suitable to be used on embedded systems, for instance, or any other system for that matter. And the good thing about it is that you can immediately start scripting with PLY, and very easily, right? Although the capabilities, again, are not as extensive as you would get with BPF trace. So what I'm going to do today is that I'm going to show you how to write scripts that would, for example, give you outputs such as the following. This here tells you that the network received related interrupts, 197, 186, and 185 interrupt numbers, right? How much time it took for them to handle the interrupt request, right? And this is a histogram telling me that interrupt 185 on CPU 1 was triggered 4 times, and it took between 8 and 60 microseconds to handle that interrupt. 2 of those 2 times, and it took between 16 and 32 microseconds, and then 5 times, which took between 32 and 65 microseconds for it to be handled. So this is very interesting information because it tells me if I have any latency, any out of the ordinary latency in my network receive chain, or any other interrupt for that matter. It doesn't have to be network interrupt necessarily. And this is useful in real-time systems because you want to know how much time it takes for you to actually handle an interrupt request. And also useful in networking, for instance, when you have a high demand of, when you have a high number of packets hitting your network card and you just can't keep up with processing them, right? I'm going to drill down into the details of how I did this, but before that, I just wanted to show you the end result, right? Okay, so the end result is we're going to get histograms like this telling us how much time it took for us to handle an interrupt. And if you're wondering how much coding effort it takes to write a PLY script to do that, it's very minimal. It's just like 16 lines of PLY code, right, or script. But before this, let's see how the interrupts are going to be handled, right? So let's drill down just a little bit to see how Linux deals with interrupts. So I'm just going to run the perf list command, and perf is a tracer, and that's extensively used in Linux, along with many other tracers. And here are all the events that the kernel provides, and perf actually kind of provides to you as the front end. Okay, so I'm just going to look for IRQ, and here are the events of interest. These 5 events. IRQ handler entry means that the kernel entered the hardware IRQ handler routine. Here it means that it exited the hardware interrupt handler routine. Then it entered the software interrupt handler routine, and it exited it. And the way interrupts are handled in Linux is that first you get the hardware interrupt, and then that is basically handled via a interrupt service routine, which runs at the highest priority. It's very important for us not to miss a hardware interrupt, but it's also very important for us not to spend a lot of CPU cycles inside the hardware interrupt handler routine, because the hardware interrupt handler routine runs with the topmost priority in the system. So it would preempt everything, right? Because it's very important not to be missed. But at the same time, because it's running with the highest priority, it will prevent all the other threads and activities of the kernel to stop on that particular core, right? So the idea is that we want to do the bare minimum in the hardware IRQ service routine and delegate the rest to a software interrupt context. Sometimes we even go further and delegate some of those to a kernel thread, which runs at priority just like any other thread would run, right? So that delegation, when that happens, we get a soft IRQ raise right here. And this soft IRQ is basically, what it means is that I have been run because a hardware interrupt service routine has delegated some of its tasks to me. Okay, so what I'm going to do is I'm going to trace these with perf just to understand what happens, so that we can then write the PLY script. So for you to understand the PLY logic, you first need to know how things really happen in the kernel. So I'm just going to trace these guys. Okay, to do that, I'm going to run sudo perf record the trace -a, meaning on all CPUs, e meaning the following events, these events, and that's it. So these events, and you can use wildcards, right? Let's give it a few seconds, and okay, it should be enough. Stop it. This is amount of data, and then that was collected 5 megabytes, and then you can see that, oh, okay, so this is my perf data. If I say sudo perf script and I don't specify anything, it's gonna just by default open up this one. And this is a binary file, by the way. It's gonna convert it to, like, parse it, and you'll see the text here. Okay, so here we see the interrupt handler entry and exit events, meaning that the interrupt 203 was raised, that's the hardware interrupt, and then it was handled here. The hardware interrupt part was handled, right? But then it was delegated to a software interrupt. Let's find something that relates to networking. So that's vector 3. Just going to search for that. Okay, there you go. Vector 3 here. As you can see, my interrupt 185, this is the IRQ arriving, handler is entered, and then handler is exited, and then this signals a soft IRQ is raised, meaning that the task is being delegated and to a software interrupt context. The software interrupt starts to do the receive part and then exits here. The reception is done, and by the reception is done, meaning that basically layer 2 is finished, roughly speaking. So this is the point, roughly speaking, this is the point when the packet is handed over to the IP later. Okay, so all the processing related to the DMA, well, actually DMA happens before that, reading from the DMA buffer, and then the driver and layer 2 and everything, link layer, is usually what happens inside this, roughly speaking, is what happens from here to here. Okay, so if I want to know how much time it took to serve this interrupt, then I should compute the difference between this time that the interrupt was raised, hardware interrupt, until the software one was exited. And this is basically 512 microseconds. This is 546, which is about 34 microseconds, right? But the hardware interrupt took only 1 microseconds to execute, which is way less, right? This is the hardware interrupt part. So let's look a little bit here. This tells me what process was running, what was the PID. This is the core that this event happened on. This is the time since boot in seconds dot microseconds that this event happened, right? And then this is the events. Okay, so what I need to do is that I need to only intercept these 5 events and basically compute the difference between the exit and the entry in PLY. And that's exactly what I'm going to do with my script. So here's my PLY script. Okay. Well, I have 3 trace points blocks, if you may, right? And here I'm just saying, hey, PLY, I want you to execute whatever code is between these curly brackets when you encounter this condition, when this is triggered, right? So I'm saying, okay, this is a trace point, IRQ/IRQ handler entry, right? If you remember when I did sudo perf list, let's just grep for IRQ. Okay, these were the events that I had: IRQ, IRQ handler entry. So it's part, this event is part of the IRQ subsystem. So this is how we show it. This is the IRQ subsystem slash IRQ handler entry. Same thing as this guy, right? So this is a trace point that I want you to trigger upon. Okay, what? And then the slash is basically saying that when you trigger upon this trace point, make sure that the condition after the slash is true. Otherwise, just skip it. Okay. So all this condition is saying is that I want the IRQ number to be between 185 and 200, because that's my interrupt request lines related to my Wi-Fi network card. How do I know that? Let's say, okay, I do cat proc interrupts. Here, I have all the list of interrupts, right? All the list of interrupts and what they mean, okay? And if I scroll down, I can show you that interrupt 185, right, is related to my IW Wi-Fi. Interrupt 186 is also related to that, and then down to interrupt 200, okay? So they're for different queues of my Wi-Fi card. So from 185 to 200, those are the ones. So what I'm saying is that I want the IRQ to be between 185 and 200. Okay, and I'll tell you why I do this data points to IRQ, right? Obviously, this data is a pointer. I'll show you where I get that from. So if this event is triggered, the hardware interrupt handler entry point is triggered, and the IRQ is between 185 and 200, then run this. So this is just a map, or let's say a variable, right? An index variable, we call it a map, which is indexed by the actual IRQ number and the CPU. So in PLY, there are certain keywords. So CPU is basically the current CPU that this piece of code is running on, which is going to be the current CPU that this interrupt had happened on. So it's actually the CPU that is handling this interrupt. So what I'm doing is I'm creating a map for every interrupt and CPU, because an interrupt can be served on different CPU cores. So every time that interrupt happens, I look at the CPU core and say, okay, this interrupt on this core is taking that much time to execute, right? So here I define a map, latency, interrupt, and CPU core equals time. And this time is just another keyword, which is the current time of the system, right, in nanoseconds. So I record the time. Then that's it. Another trigger that I define for PLY is where I hit the IRQ handler exit. So this is again a trace point. So I'm telling it this is actually a trace point from the IRQ subsystem, IRQ handler exit. And I want you to trigger this given this condition. Well, you don't always have to have this part, right? But in this case, we need it. So I'm going to say, if you ever encounter the handler exit, trigger this part if latency this. This just means that there is a latency map defined for this IRQ line and CPU, because I want to make sure that when I hit this interrupt, this exit from the handler, I've already recorded the entry point. Because in the when you're starting your tracing, maybe you're in the middle, right? So you've missed the entry, but then you get the exit. You just want to rule that out, right? So in that case, I would not have defined latency, right? Then this would not be true because this does not exist, and this would evaluate to false, and it would just skip this. Or maybe it had the handler entry, but it was for another interrupt, not related to my network card, Wi-Fi network card. So again, in that case, latency would definitely not be defined because I never executed this. So I'm just going to skip those. So in a sense, this part, these conditions are kind of redundant, right? But I'm just leaving them there. Then, okay, exit from IRQ. What I want you to record is basically, I want you to record a aggregation. So this is what's called an aggregator in PLY terminology. An aggregator is basically a map that aggregates a bunch of values. Like a map is, you can treat map like an array, right? You assign it to time. But here we want to store a histogram. A histogram is not one value, it's an aggregate of values. And there are certain aggregators in PLY that you can use. If you go to the manual for PLY, and I'm just going to search for aggregations, right? So there are actually two aggregations in PLY. One is a count, it's just a counter. The other one is a histogram, which you just say quantize and then some value. So this means that this aggregate map, if you want to call it, is recording a histogram. Okay, so whenever you have a counter, you implement it like this. Whenever you want to have like a histogram of things, you implement it like this. Just think about it like that, as simple as that. Oh, what I'm interested in is having a histogram of the hardware IRQ latency. So from the IRQ handler entry to the exit. So I'm just going to say @ IRQ lat on this particular core, right? I'm just, on whatever core. Or I could say, I could also differentiate this with respect to the actual interrupt, right? But I'm not doing it. I'm just saying, well, for the hardware interrupt part, I'm just interested to know the delay on a certain core. So maybe there are 10 different interrupts that get aggregated into this histogram, right? But they all share the same attribute, that they're all served on the same CPU core, right? So I'm just saying quantize, and what is the value that I want you to quantize? It's basically the latency, which is the current time minus the time that it got into the handler. So this is latency here. I kind of defined latency as the time that it got into the handler, and here I'm just taking the difference of current time with that, right? Again, I have to refer to the interrupt and the CPU. Okay, I'm getting that and storing it here. Let's ignore this for now. And then the other trace point or the other trigger point that I want PLY to do something for me is when I encounter the software IRQ exit. I don't need to look at the raise or the soft IRQ entry. I just need to know the exit, right? So I'm saying, okay, this is again a trace point PLY from the IRQ subsystem, and the event name is soft IRQ exit. So whenever this happens, this trace point happens, start running this code. But before that, check if the data vector is 3, right? Because I'm only interested in the network receive software IRQs. So in that one, data vector is 3. Also make sure that I have the latency already recorded, meaning I have the time that I entered this, right, already recorded. And last IRQ CPU. Make sure I already have that. And I'll show you why I want this in just a few seconds. So if all this is true, then run this part. And this is where I actually compute the actual latency. So I call this, again, is another aggregate. It stores the histogram. Call it net receive latency. It's indexed by the actual IRQ and the CPU. So the CPU that I'm currently executing on, and what IRQ is it? The problem is that at the time that I'm receiving the software IRQ, I don't know what the hardware interrupt is. Because if you go back to these events, to the perf events, here, if we go back here, we can see that, let me show you, let's say back equals 3. Okay, at this point here, in this event, there is nothing in this event that would tell me, this event in itself, that would tell me what is the interrupt, the hardware interrupt corresponding to this event, right? We're not always lucky to have this process as the context in which this event happened, right? We can't just rely on this. This was just sheer luck. But I don't know. So what I can do is that look at the last interrupt that happened on my network card, on the same CPU. That's it. So that's definitely going to be the interrupt. It happened on the same CPU and it was related to networking. And I am a soft IRQ for network, vector 3, right? So it's got to be my interrupt. And that's what we do. That's exactly what we do. This last IRQ CPU is exactly that. It records the last interrupt received on that particular CPU, okay? And it's only for the networking interrupts that this is recorded, okay? So now I'm saying network receive latency of my original hardware interrupt number and this core, quantize it, okay? And again, this is going to be time, this new time minus the latency, right? And that's it. And one additional thing I do here is that, just for fun, is that if that latency is above 1 milliseconds, which is 1,000 nanoseconds, I just do a print. Like I just go and say printf IRQ is this guy, and it's on this CPU, and this is how much it took. And the V here, the %V is basically means auto, meaning that automatically figure out what is the type of this variable here, and put that as, like, format it nicely, right, based on the type of that variable. Okay, so this is all it does. Now let me run it again. So we're just gonna say sudo ply -k is basically, well, we can omit -k, right? And by the way, if you want to run ply, it's good to give it a test before -t would do the test. It verifies that everything related to ply is installed nicely. And if you do ply -h, it's going to give you the options, right? So what I'm going to do is just, I'm going to say sudo apply this guy. The -k is used sometimes. There are buffer overruns because there are many events happening, so it can't keep up, and it overruns the buffer, and it will, in this condition, it will exit. Ply would exit. But if using -k, we would say just go on, forget about buffer overruns, just continue running. In this case, it's not going to happen, so I'm just going to let it run for a little bit to collect a few traces. We'll just give it a little bit of time and then come back and see how it did. Okay, I guess it should be, oh, nice. Actually, it's interesting. It showed me that on the hardware interrupt line 192 on core 0, I had 4 interrupts which are took more than 1 millisecond. They actually took a lot of time. So this RQ192 is not very happy, obviously. Okay, so let's say that's done. And then what Ply does is that when you stop it, it will dump all the different aggregators and maps and variables that you have defined, right? So there'll be a bunch of noise here, but what we're interested in is this guy, right? That tells us the hardware interrupt latency on different cores, core 0, core 1, right? And this is the distribution. But then the entire interrupt service latency for the networking interrupts is here, is this value. And you can see that the 192 had actually 8 interrupts that happened that took about more than half a second, right? Which is really surprising. Okay. Yeah, proc interrupts. So 192 is Q7. Yeah, whatever reason this happened. So this would be interesting to look into this and see why this happened. Okay. Now I'm going to do something interesting here and put the network card under a lot of load by doing a lot of ping floods, and do this again. So we have this this set of this collection, this trace, this analysis, right? And we can see that pretty much everything is fine except this few cases of like very large interrupt handling latency for 192 here, right? But everything else is well below 100 microseconds, or in that range. Okay. So now let me run these ping floods, sudo ping -f, and then this basically tells me that send 100 pings without waiting for the response. Okay, you have to be sudo to be able to do ping floods. Let me run another one of these. Just going to run a bunch of them, just to make sure I'm putting a lot of load on the network card. Okay. So here, and oops. And I guess that's it. So let's run this experiment again. There you go. We're getting a lot of these now. RQ190 latency is above a millisecond, so we're getting a lot of these. These didn't happen a lot. Like those more than 1 second cases, those were one-off cases, which could have happened due to a different number of reasons, and they're very interesting to investigate, of course, but here we're actually seeing a lot of these violations. Now, something also very interesting, and on many of the interrupt lines. Something also interesting I want to show you is that if I do cat proc net softnet, let me just blow this up a little bit. Okay, yeah. If I show you uh, this piece of information here is very interesting. It basically tells you these are the cores, right? These are the different cores. What it does, it tells you how many packets arrive on each core, and then how many of them are dropped and how many of them are kind of hardly processed, basically. So it's telling me on core 0, I've received since boot this many packets. It's a lot. This is in hex. None of them have been dropped, right? Uh, this is all, of course, this is dropped in from the network layer point of view. If it's dropped like when it's getting from the DMA, right? It's not going to show up here. Those kind of drops are very nasty and can't be spotted. This is a squeeze parameter. This is also interesting. These two are interesting, and I wanted to show you. Squeeze parameter is when the network card, the network code, right, has a time allowance to once an interrupt hits, and I mean a soft interrupt. Once a soft interrupt is scheduled to basically process the packets arrived on the network card, so that it would copy it out of the DMA buffer into the main memory and hand it over to the kernel to the IP layer to do whatever it wants with it. That processing, there's an allowance, there's a budget that whenever you get a shot at it, right, you can exceed that budget. And if you let's say the budget is, I don't know, let's say it's 10 microseconds, right? Once you finish your 10 microseconds, you have to give the processor away to somebody else. Soft IRQ has to finish, right? And then wait for the next round for the scheduler to allow you to again do the processing. So whenever you deplete your budget, the soft IRQ, whenever depletes the budget for processing these packets, it bumps up the counter here. And these are called squeeze times. So it's actually an indication of how much pressure, how much interrupt pressure is on a certain CPU core, right? In terms of processing packets. And as you can see, it's actually the number is going high, especially on core 1, 0, and core 1. And on all the rest, we have very small number of squeeze times, right? So the budget depletion didn't happen a lot. This doesn't necessarily mean there is a packet drop, but it could happen. When this is large, right? It could well be an indication that you're having packet drops that are not accounted for because it happens before you even hand it off to the network stack, right? So it's really bad if we have high numbers here. In this case, we have these large numbers. It's not good. And if you can see that the number of packets being processed here is way large, right? So these are bad signs. Well, of course, I'm putting the system under artificial pressure, right? And I've actually clocked down my cores. And sometimes I also have to disable some cores for this to happen. In this case, I didn't. But anyways, so that's a piece of very interesting information here. And this is actually why you're getting those large time values here. When the latency goes up a certain value, you're running out of budget for sure. Let me just stop this now. Okay, now this is really interesting. You see that the network receive latency is, well, for different interrupts. Now this guy is fine, 195. These are all fine. But then from here, interrupt 192, we actually see large values, larger than, in the order of half a second to half a second to 1 millisecond, right? These are relatively large values for interrupt handling. Again, these are software interrupts. If we scroll down, 185 is in pretty bad shape, and 190. These are in pretty bad shape, okay? So for instance, we see that there are actually, if I just pay attention to everything above a millisecond, there are 79 interrupts happening served between 1 and 2 milliseconds, 23 between 2 and 4, 2 between 4 and 8, and 1 between 16 and 33 milliseconds, right? And the condition is almost as bad in for this other interrupt. So we see that there are some packets that are taking, from the moment that the packet arrives in the network card, it takes more than a millisecond, up to 33 milliseconds to actually hand that over to the network stack. That's a lot of time. That is a lot of time. And this simple PLY script is what helps me to identify this. There is no other way that I can easily identify this except using BPF. And in this case, I'm using the PLY frontend for BPF. Okay. So I hope you've enjoyed this analysis. Well, let's also take a look at the hardware latencies. The hardware interrupt latency, it's absolutely fine. It's well below 60 microseconds, and this is because, again, the kernel is smart enough to only do very, very essential stuff in the hardware interrupt routine. For instance, just the fact that some packet has arrived, it sets a flag and then tells somebody to pull that queue for further for receiving the packets, right? If it had not been for this smart way of having very short hardware interrupt service routines, then my interrupt service routines, the hardware interrupt service routine, which preempts everything on the CPU, would have ran for 8 milliseconds, 33 milliseconds. So you would actually have a freeze of 33 milliseconds on a CPU core. That's devastating. Okay, just to give you a sense, 4 milliseconds is the time slice that a process is allocated by the scheduler. So 33 milliseconds is about 8 time slices, right? Those kind of things would be definitely sensed by the system, would definitely impact the real-time nature of the system. If the system is supposed to be real-time, would definitely impact the other threads, right? Okay, this is all I wanted to show you. Okay, let me show you one more thing without going through a lot of detail. And this is the amount of time, let's say I'm interested in the amount of time that a packet spends in the network stack from the moment it's created. It's basically received, right? We talked about the reception part. Now, when it's received, it creates a metadata, or a struct. It's called the SKB struct in the kernel. From the moment that is created until the moment it's consumed, right? So I just want to know the span of time that a packet is inside my kernel until it's delivered to the application, right? To do this, I need a very simple PLY script. I'm basically going to trigger on 2 kernel functions. The alloc skb with frags. This is the function that it's a kernel function. It's not a trace point. This is just a normal kernel function, C function. It's executed whenever an skb is to be allocated. Well, the name also implies, right? So what I'm doing is I'm saying attach a kret probe here. And if you're familiar with kprobes and kret probes, it's basically any function in the kernel, or any line of code in the kernel for that matter, can be traced using a kprobe. So we're going to attach a kprobe to it. A kprobe is just a piece of code that's going to be executed. You can think of it as a jump pad, a piece of code that's executed, or anything. I'm not gonna delve into kprobes here. All this is saying is that we're gonna trigger, hey, PLY, please trigger whenever alloc skb with frags returns. K-retrobe is return, means whenever this is returning, right? And then so at the return of this, which is when the skb is created, record the time in this map. So this is just a name. I could have said anything, the name of the map, and the ret value. The return value for alloc skb with frags is a pointer to the skb. So I'm basically mapping that pointer to the time. I'm using that pointer as an index because that's going to be uniquely identifying the skb, right? So skb of that pointer is the current time. And then I'm going to attach a kprobe this time, which is going to monitor or be triggered whenever we enter a function in the kernel. And that's the skb release data. This is when the skb is going to be eventually freed. I'm done with the packet. I've delivered it to the application. It's gone out of kernel. I'm going to attach a kprobe there. So whenever this kprobe is triggered, meaning that whenever this function is entered, and I already have this skb identified here, defined, and arg0 is basically the first argument of that function, right? Whenever this happens, go and compute this aggregate for me, which is, this is just any string I can say, or I can say, this is just an aggregate, just a naming convention. Quantize time minus skb arg0, okay? And it's going to give me the time difference between when it was created and it was consumed or released. Let's run this. skb lifetime. This is going to tell me how much time my packets take to traverse the kernel, right? And this is it, diff, okay? This is the histogram. And it's interesting, 67 of the packets took more than 4 seconds, and they resided more than 4 seconds in the kernel stack, right? Let's say, yeah, here, 5,000 of those took more than a second. If I stop my pings, let me stop these pings. Do this again. Let's see what I get. Okay, good. Well, you can see that the numbers are shifted to the low parts, right? So very low, right? I do have a few taking relatively large amount of time, but not as big as before and not as many, right? Okay, so let's go back to the script and see what we actually did here. This arg0, I'm just going to try and show you where I get this arg0 from and these functions in the kernel. Let me just do that. Okay, so start a tab. Okay, so these functions, just the Linux kernel code. Okay, I'm going to find this in the kernel code here. Okay. This is the function. Let me just zoom out. It's too large. Okay, this sounds a little bit better. Allocate SKB with frags, allocate SKB with page fragments. Okay. So this allocates a socket buffer, as you can see, and the return is the SK buff. So at the end, this guy would return, sorry, that's the failure path. At the end, it would return an SKB, okay? And that's the address. So this is what retval is the address of this, of basically, sorry, retval is the return value of this kret probe, which I use as an index here, and then record the time. This is the other function. I'm attaching a k probe to it, so I'm interested in the entry point to that function as opposed to the return. And this is the function. Here is what it's defined, struct skbuff. So this is the first argument, right? arg0, arg1, arg2 is how PLY refers and indexes the different arguments. These are keywords that PLY uses. So I want to say, okay, arg0, so arg0 is what? Is this guy. arg0 is this guy, struct skbuff, skb, right? Which is the same as the return value of this one. So I'm just saying that if you're running skb release data, make sure that you have already the map for that particular sk buffer pointer, meaning that you have already allocated it here. Sorry, here. Okay, that's all it means. And then I do the difference. So that's what I'm doing here. Okay. Okay. So that's also another nice illustration of how PLY can be useful in taking very interesting time measurements, in this case, in the protocol stack. Okay, I was gonna explain where I get this data and how I get this IRQ and data IRQ, what this means. So for a trace point, this data refers to the set of arguments of that trace point, right? And here I'm saying, look at the arguments of that trace point and give me the IRQ. But what if I don't know what are the arguments for a trace point? I'm going to tell you how to do this. So let's go here. In Linux, we're going to go under sys kernel debug tracing, the tracing infrastructure. And I'm going to go into events. And you can see here that I have all those event subsystems, including IRQ. This is a folder. If I go into IRQ, you can see the IRQ events that we actually recorded. They're all here, right? Let's say I want to know what are the arguments for IRQ handler entry, okay? So here I go cat IRQ handler entry, and there are a bunch of information here, which is, of course, the format. Okay, so format. Tell me what the format is. Here's the format. Here, printed format is IRQ is integer, name is this, so on and so forth. So it's saying record IRQ, right? That means that this is the first argument, right? And this is the second argument. But if I go here, I can also see that the first argument, just ignore this part. These are common information related to a event, and these then there's a empty line, and then these will be the arguments, okay? Because these are, for instance, the PID and some other things. But then after this empty line, there will be the arguments of that event. The first argument is an integer, and it's called the IRQ, right? The second argument is a pointer to character, which is a string, and it's called name. So if I wanted to refer to the first argument, I should say IRQ, and then the second one I should say name. But then how do I say those, like how do I say look at the argument and then IRQ? I use data, right? So data is just like how this data is basically what PLY recognizes when we want to refer to the arguments, right? But this IRQ is what I get from this piece of information here. So if I wanted to look at the character string for the name, I would say data arrow name, right? But then in that case, that would be a string. So I couldn't really compare it like that. Okay, so this is how I get these. For any other event, you can also do that. So if it were for, let's say, IRQs, actually soft IRQ entry format, there would be a vec. Okay, here we have data vec equal 3. So that's how I can refer or reference the fields of a trace point, the arguments of a trace point. Okay, now I can refer you also to PLY manual for more information and some nice examples. But this is all I was going to cover in this video. Thank you. I hope you liked it, and please don't forget to subscribe to this channel and leave any comments. Thank you very much. Hope to see you next time. Bye-bye.